Hello, this is Jim Hazzard, Software Development Manager at ITASCA, and I'm just going to give a brief introduction to this webinar on the Comba constitutive model. So constitutive models are the backbone of any continuum modeling software program. In a nutshell, what a constitutive model does is give you an output stress for some input strain. It sounds simple, but of course, you can have all kinds of layers of complexity here, depending on what your material type is and how it behaves under different conditions. In the ITASCA software, right now we have 26 built-in constitutive models, and we're adding more all the time. There are also 9 models not on this list related to creep. So there's over 30 different constitutive models that you can choose from in the ITASCA software. Because we have a common framework for all of the programs, each of these constitutive models, well, almost all of these constitutive models are available in all of the programs. So the code and the behavior is exactly the same, regardless of whether you're running in FLAC 3D, FLAC 2D, UDEC, 3DEC, and so on. Of course, there are some models that are not available in 2D, and there's some models that we just don't include in 3DEC because they're more soils related. But in theory, pretty much all of these models can be used in any of the programs. One of the advantages of the ITASCA software is that it's relatively easy to develop new constitutive models. Because we use an explicit solution scheme, this means we are taking very small strain steps, very small strain increments. And because of this, it's easy to calculate the resulting stress from those small strain increments. This is different from implicit programs where they often take much larger steps and then have to do some sort of iterative approach to get back to the failure envelope and figure out what the stress increment is. So because it's easy to do this, we also allow users to create their own constitutive models. So we provide the framework where a user can write their own constitutive model in C++, compile it as a plugin or a DLL, and then just include it with the software. And people do this, and a very popular example of this is the PM4 Sand and PM4 Silt constitutive models developed by UC Davis. Another unique thing about ITASCA is that, as you probably know, we have a software development branch and a consulting branch. And the fact that these two branches work closely together really drives the constitutive model development. You will see in this upcoming presentation how a specific project that required a certain type of rock behavior to be simulated drove the development of a new constitutive model. And this happens quite frequently. And another thing that the consultants do is they force us to think about ease of use. There are lots of constitutive models out there that are complicated and very academic. But if you're using them in real projects, they need to be usable by engineers. And so this forces us to prioritize ease of use. And the P2P Sand constitutive model is a good example of this. The acronym stands for Practical to Surface Plasticity, with an emphasis on the practical. And then the final thing here is that having the consultants allows us to do testing and validation of these constitutive models by comparison with real field observations and by using these models in real projects. And again, this is what you'll see in the upcoming presentation. And so with that, I will pass it off to Christine, who will talk about the Comba constitutive model.
Welcome to each one of you. Thank you for watching this webinar. In today's talk, we will present the Comba constitutive model. It was initially implemented to study the behavior of jointed columnar basalt. The Comba model is a continuum law that can be used in large-scale simulation of rock masses containing up to 4 tight joint sets. The Comba constitutive law is available in both FLAC 3D in the zones and 3DEC in the glued block. The numerical model can, in addition, consider large-scale individual fracture. In this case, the latter are accounted for in a discrete manner. The Comba constitutive law was developed for the Baihetan Dam project. The dam is located on the Jinsha River, southwest of China. The dam itself is about 300 meters high, and the length of the crest is more than 700 meters. The rock mass at the site consists of several layers of columnar jointed basalt. The column structure is formed during the cooling of lava flow. At the site, there are several layers of this lava, and the columnar basalt there have different properties, but as you can see by the number listed on the slide, the length of those columns and their diameter are in the order of meter. Here we see on the slide also a cross-section of the valley at the location of the dam. The objective of this project were to develop a constitutive model that is applicable to large-scale analysis. Of course, given the dimension of the column and those of the dam, which is of the order of 300 meters, it becomes really a challenge to represent the discontinuities at that scale, even though they have like a large impact on the behavior of the rock mass. So we developed this constitutive law to address this challenge. Again, the model is applicable to rock masses with tight joint set and to columnar basalt in particular. And in this presentation, we will show validation for large-scale application. Here are the features of the constitutive model. It has an anisotropic elastic behavior. The matrix is characterized by a Mohr-Coulomb behavior with brittle tension fracturing, and it has direction of weakness within it, referred to as ubiquitous joint. There are up to 4 sets of ubiquitous joint of arbitrary orientation. The ubiquitous joint have normal and shear springs, and there is a Coulomb criteria for slip with strain hardening, softening, and tension cutoff. The ubiquitous joint also allow for handling creep into them. Here are some references if you want to consider reading more about the constitutive model. As you can see, the model was developed about 9 years ago, but it took some time, to build the model up and to bring confidence in its capabilities to model such tight rock mass. We are currently still working on the model at ubiquitous joint bending stiffness. The elastic behavior of the Comba model, as we mentioned earlier, is anisotropic. This is due to the fact that the ubiquitous joint have normal and shear stiffness. To develop the logic, we superpose the strain from the matrix and the joint in the global axis. And then the stiffness matrix, to characterize the behavior of the rock mass, is obtained by inversion. This is just mentioning the elastic behavior. The plastic behavior is twofold because there is plasticity possible yielding in the matrix, but also, of course, along the joint. And here we list the yield and potential function for shear and tension yielding in the joint for those who are interested. The model is applicable to FLAC 3D, which, as you may know, takes a continuum approach to model rock and soil, with only a few discontinuities that are considered in a discrete manner. 3D, on the other hand, use a discrete approach to rock masses, and it allows for many structural discontinuities. But it's important in this context to mention that 3D can also be used as a continuum in regions where blocks are glued together. So the two codes use the same constitutive law for, 3-deck blocks and in flat 3D zones. In 3-deck, if we want to use the Comba model, we typically use a dual approach, whereby a discrete approach is adopted in the near field and Comba is used in the far field where the blocks are glued together. And in flat 3D, Comba can be applied in both near and far field. We will present some validation and some application, and the protocol that we have used to validate the model is the following. We carry numerical experiment with the Comba model in flat 3D, and we compare the response with a discrete numerical experiment in 3-deck. In that technique, the Comba ubiquitous joint in flat 3D are the equivalent of the discrete joint in 3-deck, and the Comba matrix in flat 3D is the equivalent of the blocks in 3-deck. So in the setup of that protocol, we use the same elastic and strength properties for both the discrete and continuum approach. We'll present two applications. One is at the Baihetan site, and the other with the situation in a copper mine in Chile. The validation that we present on this slide is uniaxial compression on foliated rock. Advantage of this simple example is that there is an exact solution for it. And so we use this advantage to compare the response of both the continuum approach in flat 3D with Comba and the discrete approach in a 3-deck model. And here to the left, we plot the modulus versus the joint angle with just one set. And to the right is the strength versus joint angle with one set. And we see that there is a good match for both elastic and strength response in the joint. And this compares well with a Jaeger analytical solution. The second validation that we present here is uniaxial compression and plate loading test, carried out using the protocol that we have described earlier. Here, 4 joint sets are being used, and we see contour of displacement in both the 3-deck discrete model approach and in the flat 3D continuum approach for uniaxial compression and plate loading. And we see that again, we are the match in discrete and continuum model response for the displacement magnitude is quite acceptable. The larger scale validation that we present is due to Rodrigo Silva Guzman from ITASCA Chile. He did a number of large scale validation tests. Here we present the situation of wedges in a slope. And again, we compare the displacement in using the discrete approach with no Comba model, and to the right with the flat 3D approach, and the overall behavior in both cases is quite good. The next topic that we approach is an application at the large scale of the Baihetan Dam, and there the studies about the stability of large surge chambers. We use a dual discrete continuum rock representation in 3-deck. We see to the left the surge chamber that the project was all about, and they are hundreds of meters high. The Comba continuum model is used in 3-deck glued block in the far field to model the columnar basalt. But in that model, we have identified several regions referred to by the letter R, R0 to R4, where we want to analyze the situation, the stability at the scale of the discontinuities. And of course, it becomes really cumbersome to do that for the whole model at that scale, so we restricted the discrete approach to those small regions, mostly around the cap of the search chambers. Here we see the excavation-induced damage zone around the chamber, and the discrete region appear on the plot, as well as the region where the Comba continuum model has been used. And what we bring the attention on in this slide is that the depth of the damage zone in both continuum and discrete region is about of the same dimension. And there is good agreement between those results and sonic wave monitoring results. So that is very encouraging. And what we would like to point out is that shear and tensile yielding on the ubiquitous joint in the Comba continuum model, so has the same meaning as the joint slip and tensile failure in the discrete model. So we have good match of the two behaviors, both discrete and continuum in this case. The second large-scale application is the study of slope stability of a large open pit copper mine in Chile. And this study used FLAC 3D, so it's a continuum approach altogether. There at the side, there was an instability 80 meter high that has been observed after the excavation of the lower bench of the wall. And what we wanted to achieve is a back analysis using the Comba model. The structural information carried out, analysis carried out at the site give us information about the joints and faults that have been observed. And we see that there are several joint sets. The major one is, and the most relevant, is called G3, we see to the left. There is also a large fault. And in this model, we want to mention that all the large faults are modeled in a discrete manner, but the joint set are represented using a continuum approach. And what we see here that is really important is that there is a joint set that exists on site that is parallel to the main observed fault at the site. So the person, Rodrigo, who carried out the analysis, used different constitutive model for the back analysis. And he used, a hook-bound constitutive model. He used, of course, he started with a simple Mohr-Coulomb, and then he used one set of ubiquitous joint, and he was, that those attempts were not successful at reproducing the type of endommagement observed at the site. Then what he did was to insert not only the major joint set in the analysis, but also the joint set that was maybe not totally obvious by the on-site description. And when he took into account those two joint sets, in addition to the major fault, as I mentioned, he was able to reproduce the failure that was the object of the analysis. Here on the plot, what you see are contour of the factor of safety obtained by the strain reduction procedure. And what we would like to take as an observation from those two large-scale analyses is that, wandering exercise allowed by numerical modeling, it can help you validate a simpler numerical approach, continuum versus discontinuum analysis, at the investigation scale that we observe, from the first large-scale application at the Baihetan Dam. And in the second example, we see that those type of wandering exercise can sometimes reveal hidden influential feature in intriguing system that were maybe overlooked in the field characterization. On behalf of my colleague who contributed to this work, thank you very much, and we look forward to your question. Thank you.